Alright, so when before I made the harmonic oscillator videos, I was going to talk about classical mechanics, but I ran into a problem. I couldn't quite explain what the Lagrangian was and the principle of least action as a result, because there's a lot of things that are, it's kind of loaded terminology with a lot of it, like why is the Lagrangian the kinetic minus the potential energy. So I'm actually going to do the counterintuitive thing and do a rough sketch of a derivation of classical mechanics, and that from the some of the principles of relativity. Alright, and I've got some notes here that I'll be looking at, because otherwise I would go completely off track. So I spent all day writing these down. Alright. Alright. And this is, well, the notes aren't improvised, but, you know, me doing this will be fairly improvised. So, say you have three different people or things. You have Bob right here. We're going to say this is Alice. Let's go in alphabetical order. This is Alice. This is Carl. And over here you have Bob. Alright. Alice is what's called the stationary observer. Alice does not move. Alice stays put here at the origin, which we'll say is x equals 0. And Bob starts moving at t equals 0 and starts moving at a constant velocity v. So Bob is in a reference frame, so to speak, moving with velocity v in this direction. The argument applies for either direction, but for simplicity's sake. And then here's Carl. What I'm about to explain is, what does Alice, the non-moving observer, measure Carl's coordinates in space and time to be, versus what does Bob, the moving observer, measure from his point of view, measure Carl's coordinates in space and time to be from his point of view. So Bob will measure Carl's coordinates as x prime, t prime, and Alice will measure Carl's coordinates. Carl can be moving or stationary or just displaced over here or whatever, as x, t. And the transformation between those two coordinate systems is a linear transformation called the Lorentz transformation. And since they take a linear motion and transform it into another linear motion, we need these transformations to be linear transformations. So can be described by a matrix equation, basically. A x t equals x prime t prime. But we'll get back to that part in just a moment. So that I'm just kind of setting up the idea of the Lorentz transformations. The second thing, there's a different postulate of special relativity, basically, that says that if Carl's moving at the speed of light, that Alice and Bob will both agree that he's moving at the speed of light. That's actually not entirely necessary if you use this hand-wavy principle that if Carl's on Bob's ship moving with the same velocity as Carl, the measured time coordinate can't be greater than the time coordinate if they weren't moving. So time can only dilate and not expand. That's kind of hand wavy, but there's some ideas I have that make sense. But the third idea is that there exists an invariant interval on space-times that's invariant under Lorentz transformations that acts as a generalization of the arc length, the distance between 2 points in space, which normally is measured with the Pythagorean theorem. So, like on two-dimensional space, the difference in x squared plus difference in y squared. Pythagorean theorem. I didn't draw that very well. I need an eraser. That's what I need. Let's copy over a piece of paper. So we'll want, in this case, we want a generalization of that, but for space-time. So I'll say P times delta t squared plus q dx squared equals ds squared, where these are constants. It's a generalization of Pythagorean theorem to space-time instead of just two space coordinates. And the fourth idea is that the path taken in space-time is the shortest possible one, the one that minimizes this, the one that makes for the smallest interval between two events in space-time. And this is actually related to the equivalence principle, which this isn't an exact way of saying this. This isn't really exactly what there's actually multiple equivalence principles, but one way of putting it for our purposes, it's it'll straighten itself out. So imagine a particle, and just imagining a space picture for right now. A particle is bound to this flat two-dimensional surface, modeled by the piece of paper. Can you see that well? Well, by the idea that a particle always travels the shortest distance between two points in this flat space, because it's bound to this two-dimensional surface, the shortest distance between those is a straight line. But if this space were curved, and it was still bound to the surface, if this space were curved, you'd have these 2 points right here, but it can't go straight through there because it's bound to the surface. It has to go. So the only way for it to take its shortest path between 2 points is for it to travel a curved path, which, when you're viewing a curved path as a function of time, a position as a function of time, it's not going to be a linear function, because a linear function of time would be a straight line. So it actually accelerates. So the idea is that acceleration and forces and stuff like that at the same rate can be equivalent to a curvature in the space and in the space-time, and that's more fully explored in general relativity with gravity and likes. And the for our purposes, the argument's not exact because, well, like for example, electromagnetic forces don't really fall into this picture, but this is more just a kind of a rough sketch of an outline to get the idea across more so. So, just to summarize, we're about done with this first section here. I don't know how well I did it or not. So one, we want to, can you see over here all right? So one, you want to, we want to derive the the Lorentz transformations. Lorentz transformations, however you like to pronounce it. I've heard it both ways before. Then we want to derive the invariant interval, or basically the distance between space-time points. It's a generalization, at least in flat space. Generalization of arc length. We want to consider that ds, which is our invariant interval, it's minimized as a functional, because it's defined as a functional like that. And then of course the idea that a curved space could correspond to our non-inertial effects and our accelerated frame and stuff. All right, let's end that.